Welcome back to the third episode of An Introduction to R for Geospatial Data. In this episode, we'll be talking more about data structures, answering questions such as, how can I read data into R? What are the basic data types in R? And how do I represent categorical information in R? To pick up where we left off in episode 2, we need to open our R project. To do so, in the upper left-hand corner of R, we can click this drop-down R project menu and click Open Project and navigate to the folder, or find it in this list. If it's in this list for you, you can click it right here. If it's not in that list, you can go to Open Projects, navigate to where that project is, and open it. Once we've clicked to open the R project, we'll now see our Geospatial in the upper right-hand corner of Rstudio. We'll also notice that our files have switched to being inside the R Geospatial folder. We now can see the data, figs, and scripts folders we created in the last episode, and this rproj file that we created in the last episode. A reminder that the data folder already has downloaded all the different data files we'll be working with throughout this workshop. In episode 1, we learned how to use R as a calculator and worked primarily in the console window. Now we'll be transitioning to using scripts inside Rstudio. Scripts can be very valuable to us because they allow us to record the history of the different commands we've run in R and lets us rerun those sets of commands together in the future. To create a new script, there's a couple of options of how we can create a script. The first one we saw in the first episode was to click File, New Project, R Script. The other option that we can use is to click this white sheet of paper with the green plus sign, which is a standalone button for creating a new file. When we click it, it gives us the options of different types of files we'd like to create, and we'd like to create an R script, so we'll choose this first one. You'll notice now it opens the source pane and we can see the script that we'll be working in. Best practices have us saving this script to an informative name that will be useful for us in the future, instead of keeping it as Untitled 1. To do so, we can click this Save icon or go File, Save. This pops up the option to save our script. In our project structure, we've already created a folder to save our scripts called Scripts, so we'll go ahead and click on that option. And let's give this script a name. We'll call it 01 so that it goes in order, and then we'll put dash data structures.r. By convention, our scripts end in the .r extension. They are plain text files and can be opened in any text editor, but this .r lets us know that the scripting language written inside this text file is going to be R. Some other features of this file name are that it has a description of what is inside this script. So in this script, we'll be learning about data structures. Another piece is that we added the number at the beginning of the script name. This will help us order our scripts as we continue on, and we'll be able to see which order they should be executed in the future. I also use 01 instead of 1, so we continue on if we have more than 9 scripts. I'll go ahead and press save to create this. I'll go ahead and press save to save this file with this file name. The first thing I like to do when creating any script is to leave myself some information at the top. And to do so, I'll use what are called comments in R and start with a hashtag or a £. First, I'll put the name of the author. Second, I'll put the date it was created on the second line. And finally, on the third line, I'll put a description. I often also like to include my email address or other information on how best to contact me. I put a blank line in here for readability. R doesn't require I put a blank line before going on to the next thing, but it's easier for me to separate that header information from the next parts of my script. The next thing you often see in R scripts is the library command we learned about in episode 1. This would allow us to load any libraries that we need for the particular data analysis we're doing in this script. However, in this particular episode, we'll be working all with built-in structures and built-in functions that are in R. These are often called base R. Instead, the first thing we'll do in our script is to read in the data. To read in our data, we'll be using a function that's read.csv, and we'll be reading in the data Nordic data CSV. So in parentheses, we'll tell it that our data is in the data folder, and then a / to separate the name of the folder from the name of the data. And then we'll type nordic-data.csv. If I ran this line of code as is, you'll note that Rstudio is popping up some helpful information here about what the requirements for the read.csv function are. If I ran the line of code as written, it would read in the Nordic CSV data file and print it out to the console when I run it. However, as we talked about in episode 1, I want to be able to reuse that data, and so I need to save it to an object in R. So I'll edit this line of code by clicking into the front of it, and I'll add the assignment arrow. And then I'll assign this to an object called Nordic. Again, the spaces here are optional, but they make for better readability for us humans. Another nice trick for reading in data, if you don't know exactly where to find your data, is to use tab completion. So let's delete where to find this data that we typed in, and I'm going to hit the tab button inside here. And you'll notice it pops up a menu with all the options of the different folders. It starts from that R Geospatial folder because we set up this R project and it knows that we're working inside this R project. And so all of these folders and files are within our R Geospatial project folder. And then we know that our data is inside the data folder. And so I can select it and click it and it'll fill in for me. And if I hit tab again, now it's showing me the items that are inside my data folder. And I can scroll down and click on Nordic data.txt. You can also start to write part of the text if I know it starts with NOR, and I can press tab and it'll fill in with anything that it matches that pattern. And I can choose the option I want. Now that we've played a little bit with how to find our data, let's go ahead and run this line and read in the Nordic data into R. So to run this line in our script, we actually need to send it down to our console. I rearranged my width here a little bit so we can see a little bit more of the console here. To run this line of code in our console, we can press Command or Control Enter depending on whether you're on a Mac or a Windows machine respectively. So I'll press Command Return because I'm on a Mac. And now you'll notice that it popped that line of code down into the console and ran it and gave me back a new clean prompt inside the console. In the environment panel, we can see that now we have the Nordic data object. This object is what's called a data frame, which is the structure that holds tabular data in R. And we can see a little bit of information about this data frame, that it has 3 observations and 3 variables. The 3 observations tells us that that data frame, that table, has 3 rows, and then the 3 variables tells us that it has 3 columns in that table. Rstudio also allows us to do a little bit of data exploration with the data table. Here in the environment panel, we can click this little play drop-down menu, and we can see the information about the columns listed here. So this data table has 3 columns, one called country, one called year, one called life expectancy. And then it shows the previews, the first few values. Since there are only 3 here, we can see that we have Denmark, Sweden, and Norway, and all the observations are in 2022, and it has 3 life expectancy values as well. This doesn't look like we're used to seeing a data table, so there's another option for how we can preview this data. If we close the drop-down menu here, we can also click on the name of the object itself, so Nordic here, and it pops up what's called a view of the data table. You'll notice in the console when I clicked on it, it typed in this view command and ran it. And what that view function did is it popped up this window here in my source pane here, where I can see the data table in a form that probably looks a little bit more familiar to me. I can see the rows as rows and columns as columns. I'll go ahead and close that preview. Let's explore this data table a little bit more through the code itself. Created a few blank lines here. Let me also add a line above reading in the data table with a comment. Let's say I'm going to read in the Nordic data. Comments can be very helpful for you in knowing what's going on in your scripts. So next, let's look at a column of the data. To do so, we can call that Nordic object again, and we can use this $sign notation at the end of the Nordic data frame's object name. And here you can see it lists each of the columns. And so let's look particularly at the country. I could click on country here or use my arrow keys to choose the variable I'd like to look at, or I can continue typing the rest of the name. When I run this line, again using the command or control return option, I'll run this line of code from my script into my console. It ran it, and it prints back the contents of the country column. We can also look at a different column. Let's look at the Nordic $life EXP, which stands for life expectancy column, and I'll go ahead and run this with command enter. And here it prints out the values that are in that life expectancy column. We can also do calculations on using a particular column. So let's say we want to add 2 years to each life expectancy value. We can take the Nordic $life EXP and then type +2. And run a calculation similar to how we were doing calculations in episode 1. Let's type command or control enter to run that particular line of code. And now we can see that all of the values are 2 values higher than they were before. Note when we did this calculation, we didn't actually change the life expectancy data. We printed out the life expectancy data with that calculation. So if we actually go and let's preview our Nordic data again by clicking on its name here in the environment panel, you can see that life expectancy is still set to the original values. However, we previewed it, we saw what the numbers would be if we added 2 to them. If we wanted to save these new values, we would have to assign them back to an object. We'd have to use that assignment arrow to save them to an object so that we can continue forward using the values that were 2 higher life expectancies. Let's see what happens if we try and add 2 columns together. Let's try adding the Nordic life EXP column together with the Nordic country column. Let's go ahead and run that line. And when we run it, we get an error. It says non-numeric argument to binary operator. This error message is not super clear, but what it's telling us is that we're trying to add something that is not a number to something that is a number, and it doesn't allow us to do that. We could, however, add the life expectancy value to the year column because both of those values are years. Let's explore a little bit more about the different types of data. First, let's look at the types of data we have in each of our columns. Let's leave a note, types of data, and we'll use a function that's called class to let us know what's the type of data in Nordic $life EXP. And when we run this line, it prints out some information in the console that tells us that the data in the life expectancy column is a numeric type, which means it's a number. There are 6 main types of data: numeric, integer, complex, logical, character, and factor. Let's explore a little bit more in these different data types. First, let's look at the class of 3.14. When we run this function, we see that it is also a numeric. So that's the numeric type of data. Next, let's look at an integer. So we'll type class, open parentheses, we'll type 1L. This L suffix forces the number to be an integer, since by default, R uses float numbers, which means numbers that have a floating decimal point or decimal points. So if we go ahead and run this, we'll see that the class of 1L is an integer. Let's leave ourselves some notes here. You can also put notes at the end of lines by putting a hashtag, and now everything after the hashtag will be ignored whenever we try and run this line. This one is an integer. The one above is a numeric. And if I go ahead and rerun line 22 by typing command return or command enter again, I can see that it ran exactly the same way as before. It printed the comment out, but it ignored it. It didn't try and interpret that as a particular function or command. All right, as we continue to explore different data types, let's look at a complex number. We'll type class 1 plus 1i. So this has an imaginary number as part of it. This is a complex, and if I go ahead and run this line, I'll see that it is the complex type. The next class we've seen a little bit of before. It's the logical data type. If we type class and we type true, we saw this logical data type before when we were doing comparisons in episode 1, where we asked, is 1 equal to 1? Is 1 greater than 2? And we got back true or false. So if we ask for the class of true, we'll see that it is the logical data type. Another name for logical types in data science is often Boolean. Expanding our knowledge of data types, let's also look at what happens if we look at a character string. So this time in parentheses, we'll type banana. And we'll go ahead and run that line. This one is what's called a character type. So it tells us that it's a string of characters. Otherwise, for us humans, it's a word. This last data type of factors can be a little bit trickier. It's not as familiar to us from math. However, it is what we consider to be a categorical data type. So this is when you may have sets of characters that represent categories. Maybe that's a state or a region that you're looking at. So the labels of your observations may have which state they come from. That's really a category rather than a set of characters. Sometimes they can be used interchangeably, and sometimes having that type of factor that is the categorical data type can be helpful for applying specific functions to your data types. Here we'll type class. This time we're going to make banana a category, so we'll wrap it in a function called factor. This time when I run class, you'll notice it prints out factor as the type. So we converted the banana character string into a type by wrapping it in that factor function. Now as we start to look at more data types, let's read in that Nordic 2 data set, which has more data included in it. Here we'll type Nordic _2. That'll be the name of our new object in R. And we'll again use the assignment arrow and type read.csv. And then in quotation marks, we'll say we want in the data folder. And this time we want Nordic-data-2. And so that I can double check that this is a real file, instead of typing .csv, I'm going to press tab. And since it filled in for me, I know that it actually exists. I thought the file name ended in .csv because I know it is actually a comma separated value file, so that's a table that's separated with commas. However, it looks like the extension is actually .txt. This is because a CSV is actually a text file. It's plain text, but it's in the format of comma separated values. So for our purposes, even though it ends in .txt, we know it is actually a comma separated value table, and then we can read it in with .read CSV. The new Nordic_2 data frame is read into the environment, and it has 3 rows and 3 columns, which we can see in our environment panel. Let's see if the data types are the same. We'll type class Nordic_2 $life exp, and we'll go ahead and run that line. And we can see that now the life expectancy in Nordic 2 is actually characters, which is surprising, right? We would expect that life expectancies would be numbers. Let's take a look at why this is, and since our data frame is relatively small with only 3 observations, we can print out the values of life expectancy. Type Nordic_2 $life expectancy exp. We'll run that. And here we can see the values for the first 2 life expectancies are similar to before. They were 77.2 and 80. And the last one, however, had text in that column where it says it's 79 or 83. And since this column had text in it, when reading it in with read.csv, it instead guessed that the data type would be characters instead of numbers. Oftentimes, it will default to characters if it encounters any text that's unexpected. Character is often the safest data type as it avoids losing any information by trying to coerce the type into a different form. Let's learn a little bit more about this idea of coercion and coercing a particular type of data into another type, and learn a little bit about another data structure in R called vectors. Let's make a few blank lines to continue our work, and let's talk about this idea of type coercion, that is, coercing one data type into another data type. So far, we've been working with single observations saved as objects, or data frames, objects that contain rows and columns. Inside those data frames, we've actually been working with the type that's called a vector, which is a group of items in R. So each column, each variable in our data frame is in itself a group of items or a vector. We've been accessing these vectors using the $ notation to check the various types of data. Let's work with a single vector here. We'll say my vector, and to it we'll assign, and then we'll create a vector by typing vector, open parentheses, and then we need to tell it how long to create this vector. And you'll notice Rstudio is giving us a little help with what the different inputs, also called arguments for this function are. It says mode by default is going to be logical, so it's saying by default it will create a logical vector, and that it'll create a vector of length 0 by default. And so let's have it create one of length equals 3 instead. We'll leave the mode in the default one, and so this should make a vector of length 3 that contains logical values. So when I ran this line, you can notice that now in my environment, I have this new vector here, and it gives us a little preview of the environment. It tells us that it's a logical type, my vector. It has 3 items in it, and those 3 items are false, false, and false. We can also print the contents of my vector by including it by itself on a line and running that. We can see that it's false, false, false. Let's make this time a character vector. Let me add a note here. Vectors and type coercion. Let's make another vector. We'll call it another_vector. we'll use our assignment arrow. This time we'll call the vector function. And this time let's make it where the mode is equal to character instead. So instead of being a logical, this will be a character vector, and we'll say length is also 3 again. So this vector should have 3 items in it, and they should all be characters. This time when we run that line, we can see another vector pops up in our environment. It's a character vector with 3 items in it, and they're all empty character strings. As we've started to work with vectors, which are actually the columns of the data frames that we've been working with in the past, those are vectors inside the data frames. You'll note that vectors always have to have the same type of data in them. So let's play a little bit with creating some vectors that have mixed types of data and see what it does if we try and create a vector. So let's create this combine underscore vector, and to it we will assign a vector we're going to create ourselves using this function called C, which stands for concatenate or combine. And to it we will list the items we want to include in this combine vector. So we'll include the number 2, the number 6, and the number 3. Let's go ahead and create this vector, and then on the second line we'll print out that vector, combine vector. If we'd like to run 2 lines at the same time, we can highlight them and press Command return, or click this run button in the upper right hand corner of the source pane. And so here it ran both lines. It created my combine vector, which now I can see in my environment panel, and it also printed out the result of the combine vector. In my environment panel, I can see that the type of this combine vector is actually a numeric, so it's seeing them all as the numeric type of data. Let's mix up the types in this next vector we create. We'll call this a quiz vector. So we'll test something out. We're going to quiz ourselves here. And to it, we're going to assign a vector we'll create using that C function again. This time we'll say 2, 6, and then instead of typing 3 by itself, we're going to wrap 3 in quotation marks. Before we run this, quiz yourself and guess what type of data do you think the quiz vector will have when we run this line. Let's go ahead and give it a try. I went ahead and ran quiz vector, and now you can see in the environment pane, it has all of the items are now characters. Let's test that by typing quiz vector and running that line as well so we can see the output in our console. Now you'll note that even though we typed in 2 and 6 as numbers by themselves without quotation marks around it, it guessed they were all characters. This is because all of the items in a vector have to be the same type, and so these numeric values that we originally typed in, 2 and 6, were coerced into being character values. Oftentimes, anytime there is a character in the definition of a vector, it will make all of the values characters. This is in a way a safe type because it avoids losing information about what that particular value was. And later, characters that are actually numbers could be coerced back into being numbers. Let's try another coercion vector. We'll call this one coercion vector. Coercion vector. Again, we'll use our C to hand create this vector, and in it, the first item will make A, and the second item will make true, that logical type we saw before. Before we run this line, guess what type you think the coercion vector will be once we run it. And remember, we learned in episode 1 that we can wrap this in parentheses to create that object and print it out at the same time. Before we've been creating it and then printing out the item in 2 lines. This will allow us to do it in 1 if we wrap it in parentheses. And I'll go ahead and run this line. And we can see it guessed that safest type. It converted our logical value to be true. So far, we've mostly been looking at the coercion of vectors that include strings. Let's see what happens when we put together a vector that includes a number and a logical value. We'll call this another coercion vector. And to it, we'll assign, using that C function, 0 and true. So this one contains a number and a logical value true. If you were to guess, what do you think will happen when we run this particular line? Let's wrap it in parentheses again so that we can print it and assign it at the same time. All right, let's see what happens. This one might be a little bit unexpected for us. So it didn't guess them to be characters, but instead it actually created them as numbers. So if we look at another coercion vector, it's a numeric type of data. And so it actually interprets these logicals as numbers when they're in a vector with other numbers. And so true stands for 1 and false is 0. And so anytime you coerce a logical into a numeric vector, it will change true to 1 and false to 0. Let's review the coercion rules. So logical can be transformed into integers, can be transformed into numeric, can be transformed into complex, can be transformed into character. So this is the hierarchy. If it sees these different types, it'll always go to the one to the further to the right. Before I said that we could take those coerced numbers that were saved into character vectors into numerics. Let's see how to make that conversion. So first, let's make a character vector example. In this character vector example, we'll say C, and we'll have a 0 in quotation marks, a 2 in quotation marks, and a 4 in quotation marks. Remember, if even just one of these is in quotation marks, it will make a character vector. We're going to define them all as characters just to be on the safe side. So we've created this another character vector or character vector example. Here we can see 0, 2, and 4 are character vector. If we would like to switch it into numeric, let's save that as character coerced to numeric. And so here we can use the function that's as.numeric, and we'll call that on our character vector example. Make this a little wider so it's not wrapping around. When I run this line, that as.numeric function converts all of our character vectors into numbers. You have to be careful with this. If you actually had values that were not actually numbers, it would give you issues. But here, let's look at, now we're getting to the point where our environment has a lot of different values in it, so we definitely want to print it out. Specifically by putting it on this line and running it. Now we can see that they look to be numbers because they don't have quotation marks around it. We could also find that out using the class function that we used earlier, character coerced. And you can see it's starting to fill this in for me so that I don't make any typos. I'm going to go ahead and press enter. And I'll run class on it. Another useful way to print out a particular vector is to use str, which stands for structure. And it will say we want to see the structure of the character coerced. And I'll go ahead and let that autofill for me. And here I can see the same information I see in the environment panel here about each of my vectors. but it's getting hard to find my vectors and separate them from one another. So here I can print out specifically the character coerced to numeric option. Let's also see what happens if we coerce the numeric values to a logical. So we'll say numeric coerced to logical, and to it we'll assign, using the function as.logical, and we'll take the numeric version of it, which is this character coerced to numeric. So character coerced to numeric. And I'm going to wrap this in another set of parentheses. That way it will print out the result and assign that to the new vector name at the same time. And so here we can see somewhere in this list of environment, now I have a new one called numeric coerced to logical, and it has the values of false, true, true. And so you'll note when we coerced numeric values into logical, when it was 0, it said false, but if it was any other number, it created true. This can be useful for us in some settings. Other times we may want to be careful about coercion. Something else we may want to note about working with vectors is another use of this combine function is to add on additional values to an existing vector. Let's make a few lines and we'll add items to existing vector. For this, we'll create a new vector called AB_vector. And to it we'll assign, using that C function, A in quotation marks and B in quotation marks. And I'm going to have this print by wrapping it in parentheses again. So I'll go ahead and create that AB vector. It conveniently is the top vector listed because it's alphabetically first. And it shows me that now I have a new vector with A and B in it. Now I want to combine that. Let's say I want to create a new vector. So I'll say combine example. And in it, I'm going to take C and I'm going to put in AB vector as the first item. And then the second item I'm going to put as DC. So it's a single value, but it has both the letters D and C in it. And I'll surround this in parentheses again so that it will both assign to the combine example vector and print the combine example vector at the same time. Now we can see my new vector has A, B, and then a third item that is DC. Another way we could create a vector of numbers would be to use the seek function. So we could create my series, another vector, by saying seek, and then we'll say to 10. And this should give us a vector. And this time I forgot to print it out at the same time. So I'll type my series and print it. Now I have a vector with the numbers 1 through 10. Seek takes a variety of different arguments. If you wanted to say, get the vector from 2 to 11 or different values, or skip every couple values, it takes several different options. If we'd like to look at the first few items in a vector or a data frame, you can do so using the head function. So let's say the head of my series. And let's go ahead and run that. By default, it will give you the first 6 items. We can change how head runs by adding a different argument. We'll say my_series, comma, n equals 4. And if I run this, it'll give me the first 4 items. Alternatively, the opposite of head is tail. So I could do my series, comma, n equals 4 for tail. and it'll give me the last 4 items in this vector. This also works on data frames. Alternatively, I might want to know the length of a particular data frame. So I can type length my series, and it will print back how many items are in that particular vector. Next, in data structures, let's talk more about factors. That's that categorical data type we talked about before. Let's leave ourselves a note that we're going to talk a bit about factors. As we explore factors, let's make ourselves a vector of Nordic countries. We'll use that C function to create our vector, and we'll say we want Norway, comma, Finland, comma, Denmark, comma, Iceland, comma, Sweden. Let's type Nordic countries, and if we run both of these lines, we can create our Nordic countries vector, and we can see the resulting values inside it. So again, when we created this is actually a character vector. Let's check it out by using that structure command again, Nordic countries. And so here, if we run that, we can see that this is a character vector that we created. But let's convert it into a factor instead. So this time we'll make it categories is the name of the factor we'll create. And we're going to take the factor function and run it on Nordic underscore countries. So I'll run that and I'll print out categories. So when it prints out categories, we'll notice that it looks a little bit different from how it printed out when it was a character vector. So when it's a factor, it's actually recoding these categories and saving them in a smaller way. When it saves each of the character vectors, it has to save each of those letters for each of the words. Whereas when it encodes them as categories, it creates the unique levels, the unique categories. And then the first one it encodes as 1, the second one it encodes as 2, the third one it encodes as 3, fourth, and fifth as it goes on. And so let's now look at the structure of categories. Our categories factor. And here you can see it's a factor with 5 levels. It starts to print them out, but it doesn't print out the whole thing when we print out structures here. And then you'll see it lists some of the data here. It says 4, 2, 1, 3, 5. And this is because, like I said, it's encoding them, the values that are in this factor, as numbers here as it stores them. So then when it looks up 4, it looks up the 4th level, 1, 2, 3, 4, so that it sees that one as Norway. This one it sees as Finland, Denmark, Iceland, and Sweden. And you'll notice the levels actually got recoded into alphabetical order, even though we didn't enter them in alphabetical order. So some things to watch out here with factors is when we try and coerce them. So let's see what happens if we try to coerce the factor into a numeric vector. So I won't assign this to anything, I won't save it, but I'll type as numeric, and then I'll run that on our categories. And you'll see the resulting vector is the numeric values. It lost that information about which of the levels it was connected to. And so occasionally, if you try and coerce a factor into a numeric, you might actually lose some information about how each of those values match up with their actual level. You can also reorder factors. I mentioned that it by default orders them in alphabetical order. Let's reorder a factor. This can be helpful if we have a factor and, for example, we want it to plot in a certain order. We can reorder the levels and then it'll plot in the order that we've re-leveled it in. So let's create my data factor. Create a my data factor. So my data assignment arrow C, open parentheses, case, and then control will be our second item. We'll have another item called control, and then our last item will be case. So here by default, case should actually become first when we make this a factor, but we're going to tell it that we don't want it to. So we'll say factor ordering example, and we're going to create a factor from the my data vector. And here we're going to specify the levels. So levels equals, and we have to use our C to put two things together here, combine them. First, we want it to be control first, and then case. And if I go ahead and run this line, I actually got an error, and it says object my data not found. And that's because I ran this factor ordering assignment trying to use my data, but I actually forgot to run the line above 82. So you might find yourself accidentally running these out of order sometimes, which is why we want to write the script in order so it can be executed top down. And so now I'll run line 82 and then line 83. Oh, and here the issue is that I have an underscore in the second use of it, and it doesn't actually have an underscore. So I'll rerun that. Now I've reordered my factor, and if I look at the structure, str of factor ordering example, I can see that it's a factor with two levels. Control comes first and then case, and then I see 2, 1, 1, 2 because case is actually listed first, but it's level number 2. All right, let's explore one final data structure before we finish this data structure section. And those are what's called lists. This can be a little confusing because what we see as a vector is kind of like a list of items in the general use of the word list. However, list itself is a specific data type in R. And where we said vectors had to have all the same type inside them, lists actually can have a combination of types inside them. So it can be really helpful for grouping things together that are different types. So let's do an example list. We'll say list example, assignment arrow. We'll use the list function to create a new list. And let's mix together a bunch of those types. So we'll say 1 is the first item. The second item will be A. The third item will be true, a logical true. And then the fourth item, let's actually make the third item a numeric vector. So we'll use the C to create a vector. And we'll say 2, 6, 7. And I'll run that line. And then let's print what the list example looks like. So we'll run it by itself. And so here with lists, the items are numbered and they have 2 brackets around them. So the first item in our list has a 1 inside it. The second item in our list has an A. The third item in our list has a true. And the fourth item in our list has a numeric vector with 2, 6, and 7 in it. So it's very interesting that these list types can contain vectors themselves. And in fact, that is what a data frame is under the hood. It is a list that has many different vectors inside it, and each of those list items is named. Those are our columns that we're seeing. So if we look at Nordic, for example, each item in the list is a named item here, country, year, life expectancy. And those items then contain a vector. This concludes the Data Structures episode of the Introduction to R for Geospatial Data lesson. Please continue on with the next episode to learn more about R basics for geospatial data.